Good afternoon. We are the Mars Rover Resource Utilization Team, and today we will be presenting water, ice, and in-situ resource analysis at Arcadia, Planitia.
Hi, I'm Jacky Law, a junior at Lowell High School in California.
Hi, I'm Symone Henry, a senior at Classen School of Advanced Studies at Northeast High School.
Hi, I'm Grace, a senior at Adlai Stevenson High School in Illinois.
Hi, my name is Annika Sachdeva. I'm a junior at Pinecrest School.
Hi, my name is Jayla Edwards. I'm a senior at Liberty High School.
Good afternoon. My name is Ian Nelson, and I'm a senior at Grace Brethren Junior and Senior High School.
Our mission goal is to send a rover to Mars in order to conduct scientific investigations. But first, we have to understand Mars's background and what we hope to find there. There's strong evidence to suggest that around 3.5 billion years ago, there was liquid water on Mars, and this is when we expect that there was life. Unfortunately, these habitable conditions came to an end as Mars's atmosphere became thinner over time, causing liquid water to boil due to a lack of pressure and making Mars basically unlivable. However, we hope that signs of life are preserved in Mars's ice, which is part of what we hope to send a rover to look for.
Our mission objectives are to determine whether life arose on Mars, characterize the climate of Mars, characterize the geology of Mars, and prepare for human exploration in the future.
So, what is ISRU? ISRU stands for In-Situ Resource Utilization, and basically this concept encompasses the idea of using resources that are already present on Mars. This is useful because it reduces mission costs, and it minimizes the amount of cargo needed on the initial mission, since resources present on Mars will be used. Since it takes 6 to 8 months to reach Mars and only 40% of missions have succeeded, we feel that in-situ resource utilization would be a very useful tool, since planned resupply missions take a long time, and ISRU can be used for material in the meantime to sustain human life for a longer time. Various minerals can be used for infrastructure, fueling, and water ice is essential for life as well to sustain the human life environment.
Mars has many minerals that we could use to establish and sustain a civilization on the planet. For example, minerals such as olivine, hematite, pyroxene, and amphibole could be used in the construction of buildings, roads, and power sources. Oxygen can be produced using the minerals olivine and hematite, and ice could be used for cleaning out toxic materials in the Martian soil, drinking water, and carrying out daily activities. In order to move forward, it is important that we look back to what was done before and learn what doesn't work and what does. For this rover, we looked at 2 missions in particular. The first is the Phoenix Lander, which is the only spacecraft to have landed as far north towards the poles as any other spacecraft on Mars. The second was the Perseverance and Ingenuity helicopter, which proved that helicopter flight is possible and is also collecting samples to bring back to Earth.
Having a rover survive on Mars comes with many challenges. Mars has a thin atmosphere with temperatures that can reach as low as negative 80 degrees Celsius near the polar regions. Also, because Mars is on an axial tilt similar to Earth, it has seasons like winter and summer. We will only have 7 months to accomplish our mission because there's very little light during the winter time. Winds on Mars are also caused by dry ice supplementing along with radiation that can damage the rover's electronics.
So the question is, why did we choose Arcadia Planitia for our rover mission? There was recently a fresh impact crater right near a mound that we chose to look at, and we feel that exploring this area could lead to potential discoveries of ice and of other minerals that are important. And this is also a safer mission compared to looking in the poles because the weather is quite harsh there, and the abundance of ice and minerals is present in the area that we're looking for, so we'll get a very similar result by looking at Arcadia Planitia. Also, for the viability of future crewed missions, we need to find drinkable water, and if we can find a way to extract the water from the mix of regolith and ice, we would be able to use that as an ISRU material. We can learn more about how ice forms at Mars by looking at Arcadia Planitia, and we can also see how rovers would behave in colder environments and potentially send another mission to a polar region in the future.
Next, we're going to talk about landing and our instruments.
What is perhaps the most important part of the mission is landing the rover. The rover uses the same landing procedures as the Perseverance and Curiosity rovers. It follows a 3-step process called entry, descent, and landing, where after entering the Martian atmosphere, it deploys a supersonic parachute to slow its descent. While deploying this parachute, we remove the heat shield, allowing for automated systems to pick the safest landing location, alongside cameras like the MARTI, which captures photos of the landing site and its terrain. After that, the parachute is cut off, and they initiate the sky crane maneuver to move out of the way and safely lower the rover. All this paves the way for the instruments to do its job on Mars.
The MARDI, formerly known as the Mars Descent Imager, is a lightweight colored camera placed underneath the rover. As the heat shield is removed during the descent stage of the rover, the camera will record our selecting landed spot. The MARDI is a significant part of landing our rover because imaging data taken will allow our rover to locate the most optimal path for the rover to traverse through loose debris, cliffs, and boulders that can obstruct its path.
Here we see 7 of our instruments as well as the RTG, which we will talk about later. Our rover is called HEF, Hydro Exploration of Frozen Findings, in honor of our wonderful on-site mentor. The first 2 of the 7 instruments are Mastcam-Z and SuperCam. Mastcam-Z is a mast-mounted camera, as its name suggests, that can zoom in, focus, and take high-quality 3D photos and videos. SuperCam can tell what atoms and molecules are in a rock from up to 23 feet or 7 meters away, as well as investigate the atmospheric data of Mars. Together, these instruments allow detailed geologic examination of distant objects that may be useful scientifically, but are too dangerous for the rover to approach directly. This helps us achieve the goals of characterizing the climate and geology of Mars.
So how do we keep all these expensive instruments safe? Well, we will use 3 nav cams and 6 HAV cams, navigational and hazard avoidance cameras, to tell the rover where to go and what to avoid, keeping it from bumping into any rocks or getting damaged.
One of our most important instruments is mica. It is an ice core, which means that it will drill into Martian ice sheets and analyze what elements are in the ice. These represent the atmosphere at different points in time. We can look for biosignatures, signs of life, like methane, which may indicate that there was life on Mars. Beyond that, we can collect general data about what the Martian atmosphere was like long ago. The design of mica is based off a current drill called Watson, which studies ice on Earth. A diagram of that is on the right of the slide.
The RIMFOX, short for Radar Imager for Mars Subsurface Experiment, is an electronic unit inside the rover that emits radio waves downwards through an antenna attached to the back of the rover, similar to that of a ground-penetrating radar. It provides information about the Martian subsurface by locating water, ice, brines, rocks, and other water-bearing minerals based on how it reflects. By mapping, locating, and collecting samples of these ice deposits with the mica, scientists could further study them to find evidence of past life on Mars and understand the geology of Mars. To keep track of the weather on Mars, we use the META, more commonly known as the Mars Environmental Dynamics Analyzer. It acts as a weather station that accurately keeps track of the meteorology on Mars using 6 different sensors. These sensors keep track of the air temperature around the rover, so we know when to have a scheduled heating, because near the polar regions, it's very cold and it can damage the instruments on board. It also keeps track of the dust in the atmosphere, ultraviolet radiation from the sun, humidity, heat emitted by the surface, direction and speed of the wind, and pressure within the atmosphere, which is all controlled by an instrument control unit. Inside the pressure sensor is a sky camera, which makes calibrated measurements on the brightness of the sun for predictions on solar energy at that location, tracking clouds in the sky and monitoring the dust in the atmosphere. All of these measurements of the Martian weather will be useful for future human exploration of Mars.
Along with the META, SAW ICE is a compilation of 3 powerful instruments, all of which were used on previous Mars rover missions. The Sherlock is a Raman spectrometer that utilizes ultraviolet laser in order to analyze fine-scale mineralogy and organic compounds in high resolution. Sherlock Holmes was a fictional detective who solved crimes. His partner in solving these mysteries was Dr. John H. Watson. Watson, the camera, assists the Sherlock as they solve mysteries about life on Mars. The camera on the Watson is mounted on the hand of the robotic arm, similar to Dr. John H. Watson's hand lens, to magnify and record textures of ice mineral samples that our rover HEF will observe. It also works to identify targets of interest. APXS, the APXS is formerly known as the Alpha Particle X-ray Spectrometer. It will be used on the rover to monitor different ways that water ice in polar regolith respond to X-ray and alpha-ray particle radiation in order to determine the chemical composition of the samples. The RTG, also known as the radioisotope thermoelectric generator, generates electrical power from heat. Heat is produced from the radioactive decay of plutonium-238. The RTG is the most convenient power source for our rover mission because it's lightweight, has a 14-year lifespan, and has been used on previous and successful Mars rover missions. It's also been used in satellites, spacecraft, and lighthouses.
The landing site for this mission is Arcadia, Planitia. The region has water ice present and is far enough away from the poles that the rover will not have to handle the extremely cold temperatures found in the polar regions. It is also just outside of the no sunlight zone, so that Hef will not be in constant state of darkness. As well as this, the terrain is flat and has a low rock abundance, which allows for ease of access for our rover.
So here we have an image of the map that we've created for our landing site for the Hef rover. This landing site is between a mineral-full mound and a fresh impact crater to maximize the area that we're going to be exploring. So we'll be stopping at 5 different target sites and potentially a 6th one, depending on how efficiently our rover moves. We have a 15-kilometer landing ellipse, and we'll be using the Sky Crane system by the Perseverance and the Curiosity rover to allow us to land within a small distance to the target one. So the line outlined in black is our primary mission, and the lines in blue are the extended mission lines after the 1 Martian year, which is when we aim to achieve our goals and we aim to reach our targets. So here we have a graph comparing the Hef mission to previous rovers. Our rover will be traveling 14.01 kilometers, which is more than any rover has traveled in 468 sols. If we use the improved AutoNav systems and the image processing aboard new computers, the rover can travel faster with the autonomous navigation and the autonomous processing. Here we have an image of our first target, and it's around 2 kilometers from the center of our landing site. We have labeled our first target as fretted terrain, meaning that it is a very safe area, and it is labeled Class 1 due to the fact that it's not going to be dangerous for our rover to traverse, and there is a low dust abundance and a low rock abundance. Rock abundance tends to make a rover mission more tricky and more dangerous. This location has a high potential value, meaning that its signature and its heat map indicates a large concentration of a certain compound, and in this case it's H2O concentration that's above 5%. And we plan to use the RimFacts tool at this target.
Okay. Target 2 is less than 2 kilometers away, and it's a Class 2 land type. Now, we're going to spend about 2 sols here, which is 2 Martian days. And what's so special about it is there's this random outlier of olivine in there. Now, it doesn't mean that there actually is any there, but the characteristics picked up by the Mars orbiter suggest there should be.
So target number 3 is 2 kilometers away from our second target, has dusty terrain, and is labeled a Class 2. As you can see from the picture to the right, it has a high abundance of hematite, which can be used in the production of oxygen and iron for construction.
Target 4 is less than 3 kilometers from the previous site, and it's pretty flat, but we don't have any satellite data in that specific area. So what we did is some data analysis and looked at the stratification of the basalt, as you can see by the light blue mineral colors in the graph. Using that, we can extrapolate about where the next sample should be and the next hotspot should be, which is why we picked this location.
Target number 5 is less than 2 kilometers from our fourth target. It is labeled as a Class 3 because of its rougher regolith. It has a high concentration of H2O, which could be used for ISRU potential, and it could also have a potential to find microbial life.
Hopefully, with all these valuable scientific targets helping create new discoveries, our experiment will have a large impact on advancing NASA's goals for Mars exploration. We plan to look for biosignature molecules with instruments like MICA and SuperCam, which could help produce evidence for the existence of life on other planets and help us understand more about where we, as humans, come from. By using MICA to study Mars's past climate and META to study its current climate, we can learn a lot more about how the Martian climate changes near the poles, helping future human explorers prepare for Mars. With instruments like RimFacts, SuperCam, and SAW Ice, we can learn a lot about Martian rocks and how they differ from other samples in different regions of Mars. And aside from obvious advantages like better climate preparation, we can use information about ISRU materials on Mars to help understand what resources would be available to human explorers in the future, using tools like RimFacts, SuperCam, and SAW Ice to characterize and understand many different types of Martian minerals. This mission will also help pave the way for future Mars exploration, both by rovers and by humans.
This is the initial map we drew out for Hef, and as you can see, it's way too unrealistic. We have to drive around 21 kilometers, which is not feasible with any rover that's currently built today. Its battery life, plus large distances, would cause way too much time for the mission to be completed, so we settled for a much closer mission to the mound.
So here we have an image of our original landing site in a place called Ultimae Scopuli. This location is in the South Pole, and based on Mars Reconnaissance Orbiter imaging, we have pictures of abundant ice in that area. However, there were many problems when looking at this area. We used a database called JMars, and in JMars there was a lack of data of rock abundance. This is very important to have due to the fact that a rover must have traversability of terrain. And with a lack of data on rock abundance, we would not be able to know whether or not this area is safe, because the mission that we'd be sending is quite expensive, and we wouldn't want to take any chances by sending our rover to a place where we don't have data. Previously failed NASA missions Mars Polar Lander and Deep Space 2 were actually sent to Ultimae Scopulae, and we still don't have a lot of information about these. And again, there was a lack of data about the essential Mars minerals, which is something that we needed to have in order to send a mission there.
We had a few challenges while researching this project. For example, missing data points in Ultimae Scopulae, as Annika mentioned, and in other places as well. There was hidden power consumption data for the rover that isn't published by NASA for very private reasons. We can't look at classified instruments that JPL has with modern technology, so we have to predict where it's heading next.
I'm very happy I had the opportunity to be a SEAS intern, and I'm confident that it'll give me the ability to become an aerospace engineer in the future. I would also like to thank my team and my amazing mentors, SJ, Ralston, and Hef.
During my SEAS internship, I learned the meaning of teamwork and compromise. I'm thankful for my SEAS mentors and teammates who helped me learn about Mars rover and the resource utilization on Mars. In the future, I would like to be an astrophysicist and astronomer, and NASA SEAS is bringing me one step closer towards my goal.
Being a SEAS intern has been an honor, and it will help me pursue my education in computer science.
Coming to SEAS has been an incredible experience, and I enjoyed making friends and learning from my mentors.
I want to be an electrical engineer one day, and I'm thankful for the opportunity that the SEAS internship program has given me. I learned that I love designing experiments, and that data research can be pretty fun. I'd like to say thank you to Jacky, love you parents, and thank you Hef, and thank you Ralston.
I want to send my thanks out to Todd Hefflinger and S.J. Ralston for mentoring us and giving us their valuable time and allowing us to work as a team together, allowing us to lead in our different ways, and allowing us to grow as students and as people in general. We wanted to re-emphasize our thank yous to Todd Hefflinger and S.J. Ralston, as well as Selena Miller and Margaret Baggio for giving us the opportunity to be at the SEAS internship and to meet all of the incredible people, astronauts, and mentors.
Thank you.
Thank you.
Thank you!